Good.
All right, this is group 6, and we are doing the thermal equivalent circuit model for a heat pipe-based thermal management system. I'm Andrew.
I'm Ling Tong.
I'm Noah.
And I'm Janelle.
Next slide. This is a quick summary of our presentation, the nomenclature that's going to be used in the equations, and we will have a MATLAB and an ANSYS portion. The quick summary of our project is that we are modeling an EV pipe-based thermal management system that is designed for a battery pack with multiple cylindrical cells. It is done using a thermal equivalent system that you can see in the lower left side as a model that simplifies the system and allows for calculation of temperature and heat transfer at each point. We'll be using MATLAB for calculations and ANSYS to model the system itself. All right. These are the assumptions made to simplify our heat pipe. On the right-hand upper section, you can see the diagram of the heat pipes used. And in the center, you can see the specific sizes, such as the inner diameter, the vapor space. Within the problem itself, they used Wick properties that match packed spheres equations. So we have assumed they are using a packed sphere. And we do not have any values for the internal manufacturer components of this heat pipe. So we went with an assumed 0.6 millimeter diameter and 60% porosity, which was given in the paper. They use a 20-degree cooling water, and the average temperature for the water inside the heat pipe is 35 degrees. You want to talk about the limit section? Yeah, you can go back to the previous slide.
No, stay like this. Stay like yeah. That's good. Couple new assumptions I added since the last presentation is that now the thermal resistance for the battery insulation film, conduction element, and thermal grease are all lumped into one single contact resistance term at the evaporator. And also the heat source is now concentrated at the beginning of the evaporator instead of spread across the entire evaporator section like shown in the picture. Next slide, please. So here are the heat pipe limit calculations. And from last time, now I have changed some of the parameters of the heat pipe, such as the diameter of the packed spheres, or the vapor space, or heat pipe temperature versus or heat pipe temperature. And here are some of the plots to show the overall trend when I change the parameters. Next slide.
And I focused on the thermal resistance system model, including the main 3 resistances that are summed together, one of them being the convection at the cooling water chamber, the internal heat pipe resistances as the centered copper wick and the heat pipe walls itself, and then the largest of the resistance, which is the sum of all exterior components, including the battery, the thermal grease, and the aluminum conduction plate that they used. And this yielded us a heat transfer total of this pipe of 1.13 watts. Since this number is not usually known, I also graphed a heat input, which should take the Q value and display it along a long range and give us the output temperature of the battery. And you can see in the bottom right, the values that are compared to on the paper itself for each one of the different resistances inside. And for a future work for this is to attempt to find out possibly if we can do temperature-dependent equations to match what they have done in the paper, but these might be outside of the scope of what we learned in the class.
All right, and for the ANSYS portion, again, our our goal is to simulate the heat pipe-based thermal management system for lithium-ion batteries used in the paper. And we've run into some struggles with running the whole system, so we decided to break it up into smaller pieces and analyze them one by one to see the accuracy of our ANSYS skills. And we have the same assumptions as last time with constant physical properties of water, neglecting the entropic heat. And for our heat pipe, the one in the paper uses a copper sintered wick. However, our model is wickless currently, and for our future work, hopefully we could add in a wick for that. Operating temperature in this result is 30 degrees, and material is copper. For the lithium-ion batteries, we haven't set a heat generation from the batteries yet, so we've decided to just set a high temperature of the batteries and see the effect of the heat pipe in the full model. And you can see the parameters of the lithium-ion battery taken from the paper in the white boxes, and the thermal conductivity taken from some online research we set to 400 watts per meter Kelvin.
Continuing with the ANSYS portion, like Noah said, our current progress shows that the battery has been cooled, but not with the heat generation of the battery. We're just using the max heat from the battery. And then we're still unfamiliar with the pattern of the heat pipe. Like Noah said, we don't have the wick added to it. So hopefully in our future work for our final presentation on Friday, we can incorporate the wick to get better accuracy of the results. And to further research, we want to graph the battery temperature over time. And then we also want to implement testing with the cooling channels as well as implementing heat generation with the batteries. That's it for our project. Thank you for listening.